The next challenge was ret2libm. It says I need to make a pwn. Let's go with that standard warm-up ROP thing. What was it? ret2libm. Obviously this is a play on ret2libc. It gives us some files. We have the challenge zip, a Docker file, and a remote netcat. So if we look at the challenge file, we're given the C. It's going to do some buffering. It's going to create a buffer with 8 bytes. And here's the important bit. It's going to give us a leak into fabs, which is part of libm. Then it's going to let us do a buffer overflow and then return. I ran checksec on the binary. We can see full railrow, so we're not going to be overwriting the main elf got. There's no canary. NX is enabled, so we're not going to be doing shellcode. Pi is enabled, so we need that leak. And it means we're not going to know where anything else is except for libm. And no rpath. Cool. So this is pretty fun. I like this challenge a lot. So normally, like I said, normally in this case you have a ret2libc. So you have an address somewhere in libc and people use like one gadget, or you can easily build ROP change because there's the system in libc. And you can get shell that way. But doing it on libm makes it slightly more difficult. We can't use standard tools. There's not as many write-ups. And so we have to be a little bit smart about how we do it. I found out after the CTF that apparently libc is at a known offset from libm. So you can actually still just do a standard ret2libc. I didn't do that though. I didn't realize it. I think I looked at the addresses within VMmap and I saw that they were different and I just gave up. I should have checked to see if they were at a constant address offset. But anyways, we're going to go with the semi-intended solution. So to start this, first thing I did was I checked to make sure that libm actually calls syscall, and it does. So we can do syscalls. That means we're most likely going to try and call exec.cve with bin shell. And so to do that, we're going to have a whole ROP chain, and the very last one is just going to call syscall. And then we need to exec.cve call this syscall. So to do that, we need rax to be equal to ox3b. We need rdi to be equal to the file name, so that's just bin shell. Then we need the arguments and the environment to be null and null. Cool. So the hard part of this challenge is actually getting rdi equal to file name. So like I said, we're going to overwrite this buffer and then we're going to start ropping right afterwards. If you dump out ropper, so there's a bunch of different tools you can use. There's ropper, there's rop gadget. I think there's tools within pwn debug, or you can use pwn tools. Somehow you just want to dump all the rop gadgets for the binary. I think for this dump I just used ropper and then I read it out to a text file so I can just read it, because it takes a couple seconds every time to run ropper. So if we take a look, we can see that there's 3,600 gadgets. There's quite a bit. So ideally, it would be perfect if we could. We need a couple things. We need some way that we need RDI to point to a string that says bin shell. At first, I was being a little bit silly and I was trying to write this value to the stack, or like look for a way to RDI to point to the base of a stack. So for example, maybe we could write bin shell here, and if we could get RDI to point to the start of the stack, like at RBP. So like if there was a gadget that looked like move RDI RBP, this would be ideal because it looks like yours would be at the top of the stack. So RBP is probably pointing at yours, and we can move that into RDI, and then we can just do the RIX is equal to OX, was it 3.9 I think? 3B. And then we also needed to set RDX equal to OX0, and was it RSI is equal to OX0? Something like this. But there wasn't a gadget that looked like this, so we had to be a little bit more clever with how we handle RDI. What I ended up finding was a write what where gadget. And so these are very cool gadgets, so let's actually just talk about the solution script. So we have our imports. One of the hard parts of the challenges was just making sure you're using the correct version of libm. By default, it's going to use the system libm, which probably does not match the remote one. So using a combination of pwn init and also patch elf, you can get it so that it uses the correct libc. And then I think I set the rpath to read locally, and then I also did an LD preload. And by some combination of all of those, it was using the correct version of libm. There's probably a more scientific way to do that. I just do everything. And then I check the binary. You can use VMmap to see where it's actually loading this library from to make sure you're using the correct one. Cool. This is a challenge thing. Oh, for these challenges, they're using CTF-X. Which version? Yeah, CTF-X. I think built in it has this like challenge script. Basically, I just read the lines, then I send it to subprocess Python. It executes it, and then it just sends it automatically. So I don't have to copy and paste a bunch of stuff. I use this for a whole bunch of the challenges. Anyways, we're going to open the main elf. We're going to load libc, libm. We're going to start a process. Again, I'm doing that LG preload, so I use the right version of libm, and I think pwn-init and patchelf are loading the correct version of libc. Then we're going to start the binary, set some contexting. If we look at the challenge, so it's going to give us that address of abs, and then it's just going to ask us for what we want. So I'm going to grab that value of abs. From there, we can calculate the base address of libm. I did a pwn cyclic to find where the start of our buffer overflow happens. And it happens here. I think this is probably like 16 or 24, something like that. So the gadget I ended up finding to solve this challenge was this one. So it's called a write what where gadget. And so what will happen is it'll move the contents of EDI into the address pointed by RAX and then return. And so if we actually do this, chal VM map. Let's do continue, cancel VM map. I didn't do preload on this, so the addresses are going to be, you can see it's using the wrong version of libm. So right now it's using libm 2.231, but that doesn't matter for right now. So what I wanted to do was do a write what where gadget. Like I said, I tried to write the value of bin shell onto the stack, but I had a lot of, it was just tricky. Maybe it is possible. So instead I looked for a known place where we could reliably just write bin shell to, and then set RDI equal to the address. So there's a bunch of gadgets that just do pop RDI. And so we can write an address to the stack and then do pop RDI, and it'll set RDI to that value. We just have to have a known address. And so since we have a leak to libm, we're going to look for a section that has both read and write. And so it was just this last one. I'm not really sure what's here. I mean, we can take a look. I don't think there was anything too important. 20x. And we can see this is the start, I guess, of their GOT-PLT. So we're just going to write bin shell right here and then pop that value, this address, off the stack, and we'll use that on our syscall. So I calculated that write address, again, just using offsets, and we know where it is relative to the base of libm. Then we have our gadget. One thing to note is it's doing EDI, so this is a 32-bit register instead of RDI. There wasn't an RDI one there, so we're going to have to do 2 writes. And yeah, let's start wrapping. So the very first thing that happens is, so we need to set the value of RDI and the value of RAX. So ROP tools makes this very easy. So we start ROP, we tell it, find a couple of gadgets that'll set RAX equal to this write address, and it'll set RDI equal to bin, and then the rest are nulled out. Thankfully, I got it right the first time. It's possible that, because of endiness, I might have had to switch this, but it didn't look like it was the case. And so then we just call ROP raw. We say, do this gadget right here. It's possible you could find the gadget with ROP tools, but we already had the address, so I just use this. So this will write bin to right here. Then we do it again. We're going to write, this is only the bottom 4 bits, or 4 bytes. Now we need to write the top 4 bytes. We're going to do racks. So increase the write address by 4, and then the second half of our payload, and we're going to write that there. So right now, this should say bin shell. Then we can do our standard wrapping. Again, we want RAX to be equal to the syscall for exec CVE. Then we have RDI equal to our address. So it'll just pop this write address, this address right here, into RDI. Then we're going to null out RDX and RSI. And then from there, there's just a syscall that's already existing within libm. So we'll just jump to that address and we'll be done. Let's see if this is working. Python 3. Loading the gadgets. And cool, it should have worked. And yep, we can see, who am I? We're just running on the local Ubuntu, but we can see it worked. So cool challenge. We can actually run it in GDB real quick. Let's do, yeah, I guess this should be a good address. Python 3, tmux. Cool. So I think I printed it out somewhere. Oh, the right address. We can examine 20 bytes of hex here. We can see that there's nothing going on right now. And so we did it right before we sent our payload. So after our payload, let's go, maybe, yeah, let's continue. Cool. We're about to do our payload. So this is at the very end of main. And so we're about to exit from main. Our payload has been set. So this is our ROP chain that's about to execute. Oops, we did not want that. Single instruction, so leave. So now we're going to do the first element of our payload. We can see that this is DA32C, C8. So we're going to pop RAX, which that's what we're doing. So we're going to pop a value of RAX. If we look at the stack, it's this value. So that was our write address. So we're popping that into RAX. So we're currently right here, popping RAX. Then it's going to continue. So we'll do single instruction. Then it's going to pop a value of RDI, and we can see that value is going to be bin. Cool. Now we're at that write what where gadget. So we're going to write the contents of EDI into RAX. We can see where's EDI, RDI. So this is bin shell, and it's going to write into RAX. We can't see it, but maybe I'll shrink by 1. There's RAX, so it's going to write to that address. So we'll do a single instruction. Cool. We can then look at that write address. So let's examine one string at this address. And we can see we now have bin. So we're getting there. So now we need to write the top 4 bytes. So we'll pop the next RAX. So this is just the write address plus 4. Now we're going to pop RDI. This should be the rest of the slash shell. And then we'll write that to the address. Cool. And now we're going to set up the rest of the registers so we can make that syscall. So we're popping RDX, which is 0, popping RSI, which is 0, popping RAX, which will be 3B, and then popping RDI, which will have the address to bin shell. And at this point, we just call syscall. There's stuff after it, but we don't care. And bam, right there, we have shell. So now that we have shell, we can read the file flag off of disk. So again, like I said, very fun challenge. I think everyone's familiar with how to do a ret2libc, but it was fun to actually test to make sure you actually know what's happening and set the registers yourself and pwn the binary.